expressions. So we graduate from polynomials to rational expressions. Why are they so strongly linked? Well, because a rational expression, by definition, is just a ratio of two polynomials. That's it. Polynomial divided by polynomial. So you can already anticipate we're going to be working with polynomials a lot, right? Factoring specifically. Well, everybody click everything closed, please. So today we're going to focus on simplifying rational expressions. Let's start off. Let's just take an example of simplifying a ratio, which is just a fraction without variable. You guys already know how to do that. What if we have something like, let's say, 10 over 14? What does that equal to?
5 over 7.
5 over 7, just like that. What'd you do?
Divide by 2.
You divided it by 2?
Yeah.
Okay, kind of. That's what you did in your mind, but what you really accomplished was something a little bit different. What you really did was this. 10 factors into 2 times 5, agreed? Prime factors. 14 factors into what?
2 times 7.
2 times 7. Okay, you took advantage of a property here, right? We can cancel like factors vertically, right? If I have common factors in the numerator and denominator of a fraction, I can cancel. So I can cancel the 2. 2 divided by 2 becomes 1. And I'm just left with 1 times 5/7. So my answer is 5/7. Agreed?
I agree.
Okay. Now I want to point something out. How is that different from this? 2 plus 5 over 2. Can I cancel the 2's there?
No.
Okay, people like to though. They like to try that and you can't do it. What's the difference? How come I can factor them in the top example, but I cannot factor them in the bottom example? Because they're being added. Exactly. You can't cancel stuff when it's being added or subtracted. You can only cancel stuff when it's being multiplied by everything else, right? So in the top, the 2 is being multiplied by everything in the numerator on the top, and the bottom 2 is being multiplied by everything in the denominator. So those are factors, and I can cancel them, right? Now, here they're being added, so I can't, and I can check and see. Like, I can simplify this. 2 plus 5 is just 7, and I get a 2 on the bottom, so I get 7/2 for an answer. If I canceled those 2's, I would get 5, which is wrong. It's not 7/2, right? Okay, let's take one more example that seems like this is going to be a tricky one. I'm trying to find a way to trip you up here, but don't fall for it. I can be pretty tricky. Can I cancel the 2's there?
Possibly, yes.
Okay, if you're saying possibly yes, what's your thinking?
It's because it's 2 times.
Okay, because it's 2 times 5, but you can't because there's another plus sign in the top, right? Well, look at the difference here. This is really important. You see the difference between that and our first example. In the first example, the 2 is being multiplied by everything else in the top. Here, the 2 is being multiplied by 5, but it's not being multiplied by this other thing that's being added, right? You see my point, right? So I can't cancel those because of that plus sign. It wouldn't work. If I did, what's the answer supposed to be here?
13 over 2.
13 over 2. If I did cancel those, I would get 8, which is not right.
Not correct.
Agreed? Okay. Okay, so then how about one more? How about this? What if I have 2 times 5 times 3 over 2? Can I cancel those?
Yes.
Yes, I can. Because now the 2 is being multiplied by everything else on top. There's no addition or subtraction in there. Okay? So those can cancel. Okay, let's do one more. I'm going nuts on this stuff. How about this? What if we have 2 times 5 times 7 minus the quantity 7 minus 4?
Oh, wait a minute.
I can, you're right. Because the 2 is being multiplied times the 5, and because that's in parentheses, it's a quantity, it's being multiplied. Everybody agree? So yes, I could cancel those there. It actually works. Okay? Does that help? Because I feel like that's a really common source of like just confusion for people. It's like, when do you cancel stuff and when don't you? And the simple rule is, You can cancel things only when you're canceling factors of the top and the bottom, things that are only being multiplied by other factors, right? How many factors are there in the numerator here to start with? 3. 1, 2, 3. Because that's in a quantity in parentheses, it counts as a single thing, a single factor. Okay? All right, good stuff. All right, so what are our steps then for simplifying a rational expression that involves variables, not just numbers? Same kind of thing. We're going to factor everything in the top and the bottom, and then we're just going to cancel like factors when we can. Okay? Something that we have to be careful of, though. This is not really included. Our text, I don't think, does a great job of explaining this part, but this is really crucial, and I'll prove it to you in a very visual way, so this will stick with you, right? So we have to exclude any values of x that cause us to violate a rule. There's 2 rules that we have to follow with real numbers. Let's review those. One of them is not important today, and that we'll review it anyway. You can't take the square root of what type of number? Negative, exactly.
Take a negative.
So there's one rule. There's one rule that would cause problems for us. We sometimes will eventually, when we deal with radicals later in the year, radical functions, we're going to have to exclude all the values of x or whatever our input variable is that would cause us to take a square root of a negative number, because that's forbidden. Can't do that. Do that, the universe explodes. It's a bad thing. Can't do it. So the other thing we can't do is we can't divide by what number? 0. That is important now, right? So we have to exclude any value of x that would cause us to divide by 0, right? Look at our original function here. The denominator has an x in it, right there. So what value of x could I plug in that would make the bottom equal to 0? 0, right? 14 times 0 squared is 0, right? So therefore, I have to, before I do anything, I've got to write down x cannot equal 0. That's my exclusion. I have to exclude that from the domain. Well, what's the domain? Let's review that. I'm throwing these words out there. We've talked about it, but it's been a while. Domain and range refer to the sets of inputs and outputs, right? Range is the set of output values. We don't really worry about that very much. But in math, we worry about the domain a lot. We'll probably never talk about, I don't know, a handful of times, if that, we'll talk about range the rest of the year. We'll talk about domain about 10 times a day for the rest of the year. Domain is the set of all the input values, right? This x in this case. X is our variable, our input variable, right? Everybody agree?
Yeah.
So it's the set of all the values of x that we can legally input into our function. So the default is everything, all reals. But we have to sometimes pick out a couple of them that don't work. In this case, it's all reals except 0. We can't include 0 because that makes us divide by 0 in the denominator. Everybody get that? Okay, I'll prove it to you. Let's look at a graph of this thing. Okay, so there is a graph of 20x to the 6th over 14x squared. If I drag a point along my graph, it just tells me all the ordered pairs that ant is stepping on as he walks along the curve, right? X and Y values. Look what happens when I get to 0. Oh, what happened?
Undefined.
Look at that.
Wow.
It's undefined. And look at the point. What does the point look like there compared to there? Yeah, okay, it looks like an open circle instead of a closed one, right? So that's telling us something very important. It tells us that there is a hole in the function. That's what mathematicians call it. There's a hole in the function at x equals 0. How come? Because that's where we would have to divide by 0, which you can't do. So when it says that, now everyone's focus should be squarely up here right now, because this is gold. I am dropping just pearls of wisdom. You better pick these up. So when I see something like that, 0 undefined, the y value is undefined, meaning the function is undefined there. You can't plug that value in. It's not part of the function, right? So it even shows up on the graph. Desmos is smart. It knows that we need to have that exclusion right there, okay? But now the next question is, can we write this function in a simpler way? Well, we can, right? And we've done this problem already. We did this problem last unit when we talked about properties of exponents. When we've got monomials on the top and the bottom, we can just simplify the monomials using properties of exponents. We don't even have to think about it as canceling factors, although I'll show you that it's the same thing. Let's just look at this like we would have last unit. Okay, we've got a number part. 20 over 14 reduces to what?
10 over 7.
10 over 7.
Wow.
Okay, how about the variable part? X to the 6th over x squared. Yeah, that's x to the 4th. Good, right? So we know we get x to the 4th. Now let's quickly review. How'd you get that so fast, Kendall? What'd you do?
I subtracted the x.
You subtracted it. Because what is the formula? And I'm going to give you guys a huge break here. I am such a nice guy. I can't believe I'm even doing this, but I'm going to give you an opportunity for some free money.
Yes.
Free money. We're going to do another quiz right before, just a memorization quiz, which is just a repeat of the stuff from test 6, the start of test 6. And I'll give you some test points for that. Unbelievable deal. All you have to do is memorize those 14 things that were on test 6. What were they? Properties of exponents, the polynomial product patterns, and the polynomial factoring patterns. Things that you have to know for the rest of the year anyway. It's just like memorizing a couple state capitals. Big deal, right? It's not math stuff. I get that algebra can get tricky. There are concepts in algebra that are complicated for anybody. It just gets involved. It's beautiful when you start to understand it. You start to see symmetries and you see relationships that are just amazing that math is the way it is. And you get to kind of participate in that and appreciate it, and it makes it very rewarding. But it requires a little work. Algebra can be, there's some stuff to know there. It requires some real thinking. Memorization does not. Memorization is easy. If you don't get 100% on that memorization quiz, and I don't know what to tell you, work harder, because that's a freebie. I would be, if I took that and I didn't get 100%, I would be very disappointed in myself if I were sitting out there. That would be a missed opportunity right there, because this is one where there's not going to be a retake. You just got to know the stuff going in. You get what you get. Day before spring break. Okay, we'll do that. Agreed? Great opportunity. Come in and just get 100.
Right.
Why wouldn't you? Add your grade with 100%. It counts as a test grade. Oh my gosh. I'm getting pretty, I'm getting pretty soft in my old age here. I'm just kind of getting to be too kind and generous probably, but oh well. Sometimes that comes with the territory, I guess. I don't know. Take advantage of it. Okay, so what is the property that we use there in terms of A's and M's and N's and stuff? A to, starts off as A to the over A to the N. Everybody see how that fits? Right? A is X. I've got like bases. I've got two powers with like bases that are being divided. And what's the result? A to the M divided by A to the N is A to the M minus N. There you go, right? So that's how we get X to the 4th. Okay, the other way we could do it though, and I want to show you this way too, and I think this is almost a better way. You got to know the properties of exponents, but just think of it as canceling factors. That's really all we're doing, right? X to the 6th, remember, is just this. It's just a string of 6 factors of X that are just multiplied together, right? X squared is just X times X. Well, I'm just canceling 2 factors, leaving me with 4 on the top, right? So you can think about this as I've got these factors that are being taken to powers. I'm going to cancel 2 of those out of the top and the bottom, which leaves me with 4 remaining on the top of those factors. I'm just subtracting, but it's almost easier if you think about it as cancellation like that, okay? Because then it would be easy to reverse that too, wouldn't it? What if I had something like this? What if I had X to the 4th over x to the 7. Now what happens?
It's negative, so you have to put it on the bottom.
Okay, it's negative, so I put it on the bottom, or I could just think about it as canceling. I'm going to cancel all of the x fourths off of the top, which leaves me how many on the bottom? 3. Oops, that's bad, 3. I got so excited I couldn't write the 3 there. 1 over x cubed. I get pretty excited about math sometimes. Sorry. Okay? Make sense? All right.
She's gonna get
Good.
stuff.
Good.
Sorry.
Okay, so then just real quick, here's an example of, we're going to graduate to different things now, right? So now we've got ratios of polynomials that are a little more complicated, not just monomials. So quick review of what we just said. A rational expression is undefined where the denominator is 0, right? This is kind of out of our textbook. So let's take an example like this one. If we wanted to find the domain of this rational expression, and technically it is a rational expression. I've got a trinomial on the top, and I've got a monomial, a constant monomial on the bottom, which is kind of a boring polynomial, but it is one, right? Well, what are the values of x where the bottom would be 0?
0.
Are you sure? If x is 0, looks to me like the bottom stays 5.
It needs to be 1.
Are there any? There are none. How do we know? Because there are no variables in the bottom. The bottom, regardless of what the value of x is, the bottom is always what? 5. Yeah, it doesn't matter, right? So in this case, there are no exclusions. The domain is all real numbers. Everything is fine because there are no variables in the denominator to worry about. Okay? Let's look at one where we do have to worry a little bit, though. How about this guy? Let's find the domain of this function. Well, to find the domain, I've got to find the zeros of the denominator. To find the zeros of the denominator, this is a polynomial issue, right? This is last unit stuff. If I want to find where the bottom is 0, what do I have to do to the bottom? I got to factor it and use the zero product property. Exactly, right? I got to factor it. Okay, so let's factor top and bottom. Blake, focus.
I'm telling him to stop talking.
Okay, stop talking back there. So then, what about the numerator? Numerator, can I factor that at all?
No.
No, I can't. Now let's make sure we know why. Because for one thing, x is being taken to the first power, so there's no way to break it apart. Now the bottom is different. In the bottom, I've got a quadratic trinomial, right? I've got x squareds. So when I have x squareds, there's a chance for me to break that apart into linear factors that have x to the 1 power, right? The top is already linear, x to the 1. There's no place to go. The only thing I could do is maybe factor out a GCF, but there is none. So nothing to do in the top. It's done. 9x minus 1. Okay, what about the bottom? It's a trinomial, so we can try to factor it. We might be unsuccessful, in which case it's prime and it doesn't factor, but we'll see. What would have to go there and there?
X.
X. Okay, my magic numbers would have to multiply to what?
3 and 2.
Okay, but what do they have to multiply to?
6.
No,
Negative
6.
Oh.
And add to
One.
positive 1. So on the test, when people missed these, I could see the wheels turning. They were thinking the right stuff, but they just rushed.
3.
They didn't play the sign game. Before you put the numbers in, play the sign game and put the signs in. If they multiply to a negative and add to a positive, what do you know?
3.
Plus 3 minus
Bigger
2.
numbers.
There you go. Positive and negative, and the bigger one is positive. Perfect. And now the numbers are easy. 3 and 2. Okay? So we can't simplify this. There is no cancellation to do. Agreed? Okay, but I do have some exclusions. What are the values that x cannot equal? No, 0. Okay, 0 works. If I plug 0 in, what happens in the denominator? And just test it out. If I plug 0 in for x, I'm going to get 3 times negative 2, which is not 0. 0 is okay.
So it's negative.
Oh, okay, good. It can't be 3. No, not 3. Negative 3.
Negative 3 or 2.
Negative 3 or positive 2. There you go, right? How come? Because zero product property. Once we get it factored, it's easy to find the zeros of the denominator because the zeros of the denominator are going to be equivalent to the zeros of the factors, right? You can only get 0 by multiplying when you multiply by 0. So we want to find the values of x that would make either one of those factors that are being multiplied 0, which we did. We can test them. Like, let's just pick one of them and test it. Evan, you guys are getting distracting yourself. Stop. So what if we tried 2? Let's put 2 in the bottom, just as an example. 2 squared is 4, plus 2 is 6, minus 6 is 0. It worked. We got 0, so we excluded it. You see, though, that we could not have found those numbers just by using that trinomial. We could only find them by first breaking it into factors and then figuring out when the factors are 0. Zero product property, right? That's our process. Okay, so let's try just a quick review. All this is saying, this is from the textbook. All it's saying is when we simplify rational expressions, we're just canceling like factors. The point of this slide, though, the one thing I want to point out here is that when you cancel things vertically, they're not canceling to 0, they're canceling to 1, which is why it works. Because, like if the R over R cancels to 1, then I'm left with P over Q times 1, which is P over Q. Multiplying by 1, which is the multiplicative identity, doesn't change what you started with, right? Okay, so let's try this then. What's our process? What are we going to try to do first? If we're going to factor, right? If we go back to our instructions here, what are the things we do? We factor everything that can be factored, and then we simplify by eliminating common factors. If they're monomials, we can use properties of exponents, but if they're not, we just eliminate common factors. We cancel them. But we got to get this thing factored, right? So first step is, first step is factor it. Can the bottom be factored? No, bottom's done. What about the top?
No.
It can be. Now let's try to walk through our strategy. Let's think through this together. How many terms in the top?
2.
2, right? So what's our strategy if we're trying to factor a 2-term, like a binomial, 2-term polynomial? Okay, it's patterns. There's only 3 patterns we can use. What are they? What's one pattern that could apply? I'll get you started. Sum of squares is not a pattern, right?
Cubes.
Sum of squares doesn't factor. Sum of cubes would be 1. What else? Difference of squares or difference of cubes. Okay, those are the 3 options we have. Difference of squares, difference of cubes, sum of cubes. Sum of squares doesn't factor. That's one that's prime always, right? Okay, so which one could apply here? Well, x cubed plus gives it away. What's the one that could work? Sum of cubes. Okay, let's write that down. You got to know that pattern. Again, this is stuff that's just you got to have filed away in the old memory bank. So I'll get you started. Sum of cubes is the a cubed plus b cubed pattern. Okay, what is that? How does that factor?
Is it a plus b?
There you go. A plus b times a squared
Minus ab.
minus ab plus b squared. Good. Okay, what were the ways that we remembered that? How do we look at that pattern and visually know what to do? Okay, remember our pattern here. Whatever the sign is that is our pattern, it's a sum pattern, right? We go same. Exactly. We go same, opposite. I'm just going to call it flip. And then we end up with always plus, right? Same, flip, always plus for the signs. What about the other parts of it? Well, the first one is easy. It's just A and B. In the trinomial, it's also easy. It's just the 3 ways of multiplying A and B. A times A times B times B, right? Make sense? Okay, so for us then, if we go back to this example, how is x cubed plus 8 a sum of cubes? How do I need to rewrite the 8 maybe to think about this?
2 cubed.
2 cubed. Okay, so A is x and B is 2, right? And we just follow our pattern, substituting x and 2 in for A and B in our pattern. And doesn't that just give us, on the bottom, we'll turn that into, because these are 2 things that are being added, right? For addition, we can commute things. We can change around positions for addition and multiplication, right? So I'll flip those and make that look like x plus 2. So it matches the x plus 2 that we get on top, right? And then we get a squared is x squared minus a times b is x times 2, that's 2x, plus b, which is 2 squared, is 4, right? And I can cancel the 2's. But before I cancel the 2's, I have to exclude that negative 2 from my domain, right? Because x equals negative 2 is the 0 of the one factor in the bottom, meaning that's the one value of x that makes it 0. Agreed? Okay. So my answer has two parts. It's got the simplified function part, which is this. In the assignment, that's the first thing you're going to enter in one of the answer boxes. The second part are the exclusions, and you'll enter those in the exclusion box. Okay? That's it. All right. Okay, let's look at another one. Another example. So let's try this one together, and then I'm going to have you go to the boards and try one on your own. So what do we do here first?
Factor.
Factor. Okay, factor everything top and bottom. All right, so on the top. Whoops.
What the-
I never know.
What the heck?
I don't know what I'm doing. Oh,
Watch out.
Okay, so what do I do on the top?
Take 5 out.
Take a 5 out. What's left behind?
You see it, yeah. 9-1.
Minus,
W.
holy.
there you go. 5 times the quantity, 9 minus W. Top is done. Bottom.
3.
Can I take a 3 out?
No.
928.
Slip and slide.
Oh.
Slip and slide.
Slip and
There you
slide.
go, it's slip and slide. Good.
Watch out. Stop.
Hey, please stop. What about? You don't want to know what. You don't want to do.
Okay, so you guys, please walk me through slip and slide.
3
times
times
9.
9. 3 times 9.
Okay, good. So we slip the 3 to the end and multiply by 9. Good. That gives us the basic trinomial, w squared minus 28w plus 27, right? This is the trick. This is the part that makes slip and slide an easier way to do things, because now I've got a basic trinomial to factor. So we try. If we can't, it was prime, then we give up and it can't be factored. That should be a W and that should be a W. Let's play the sign game. They multiply to,
Negative.
Negative.
Multiply 27. Minus.
good, so the negative, and what are the numbers?
27-1.
There you go. Man, you guys are, getting good at this. Good.
You're on top of things, man.
Okay, good, and we divide each of our magic numbers that we found by the number we slipped.
You slipped, buddy.
Okay, now what?
Simplify.
W minus 9.
And then 3W.
3W.
minus
Okay, good. So this fraction can't be reduced, right? But it stays a fraction, and so if there are any remaining fractions, we slide denominators up to become coefficients. So we get the other factor is 3W minus 1. Okay, good. So now we know what to put up here in the bottom of our fraction. Slip and slide gave us the answer. It is
Thank God for slip and slide.
Oh, thank goodness.
W minus 9 times 3W minus 1. Okay, now you got to pay very close attention, because this is a trick that's going to save you lots of time. Okay, is there any cancellation there?
Yes.
I mean, kind of, right? But we can't just cancel those because they're not identical.
In order,
right?
Oh,
Can we still
yeah.
flip them though?
Okay, you can't flip these, because
Right.
when there's subtraction, you can't, and I'll prove it to you.
So
Let's
that's
look
the
at,
reason we got to flip the other
like,
ones.
what if I have 7 minus 3, is that the same thing as 3 minus 7?
No.
No. 7 plus 3 is the same thing as 3 plus 7 though, right? So you can commute terms that are being added but not subtracted. Okay, so the question becomes, what do we do with that? Now let's investigate this, because whatever works here is going to work in any case where we have something like this. Something that takes the form A minus B over B minus A, where all I'm doing is I've got one difference on the top, things that are being subtracted, and I've got the flip of that on the bottom. Okay, whenever that happens, there's going to be an easy solution. Let's figure out what it is. Let's take another example, and we'll come back and use the outcome of this. What if I had something like this, 7 minus y over y minus 7? Same terms, but they're being flipped, right? Everybody agree?
I agree.
Okay, so now here's what we do. I gotta make I gotta somehow get the same factor on the top and the bottom. So what I'm gonna do is I'm gonna factor a -1 out of the one on top where the variable is negative. You could do it either way, but this way will make more sense. So if I undistribute a -1 from those terms, what's left behind? Let's see. -1 times what would give me my 7? -7. Okay, so then, so that's a -7. The first part is right. -1 times what would give me -y? Positive y, right? -1 times positive y gives me my -y that I started with. So does everybody agree that's what I get when I undistribute a -1? Okay, now can I flip those terms around? Yeah, because there's a plus sign in the middle, right? So I could do y plus -7, which is the same thing as y minus 7, right? Aha. Now this looks better. Now I've got my GCF, or it's not really a GCF, but I've got my factor that I undistributed of -1 times y minus 7 over y minus 7. Aha, look what happens. They cancel, and I'm left with -1 over 1, which is -1. Okay? We don't have to do that every time. Whenever we see something that looks like this, a minus b over b minus a, that pattern, what does that always correspond to?
-b divided by.
Okay, but what was the outcome though? What did we get down here? -1,
No.
right? Okay, so then this becomes, anytime we have that pattern, we can replace it with a -1. So here's how you show this. Now you and you guys get distracted back there. You gotta really pay attention or you're not gonna get this. It's gonna stymie you on the homework. We don't want that. So what happens here then? Look, those are flips. 9 minus w over w, or 9 minus w over w minus 9, right? Those fit that pattern. So here's how you show it. They cancel, but the arrow points to a -1.
Ooh.
Those get replaced by a -1. Isn't that slick?
That works for everything.
Exactly. So then this is going to become, what happens here then? This becomes -5 on the top. I get -1 times 5 over, on the bottom I just have a 3w minus 1. And I don't need parentheses on the bottom because it's the only thing down there, right? So that's my answer.
So the second group never changes. The 3w minus 1.
No, it's just those factors cancel to -1 instead of 1. Okay. Now I still need my exclusions though. We didn't include exclusions yet. What are the values that x cannot equal?
3 and -1. Oh no, -3 and 1.
Okay, so 9, right?
Yeah.
What about this one? Now this is the one you do in your head, but remember, here's what you do. We want to know when is that 0. So you just ask yourself, 3w minus 1 equals 0, and you just solve that in your head. I'm always just setting that factor equal to 0. To isolate the w, I'm going to add the 1 and divide by 3, right? So what do I get?
Clever.
There are my 2 exclusions, right?
Yes, sir.
Okay, you guys don't have a lot of time, but we're going to try to get this done. So jump up to the boards and try that one, quick.
Oh, you got it, Ernie.
You got it.
Oh, we're done, babe.
Oh my god, he said that.
Okay, so we already graphed our original function here, right? And we got this graph. Come on. Okay, we got that graph. The red graph was 20x to the 6th over 14x squared. Okay, and we found that had a hole at 0, right? If I can get that right there, right? Agreed? Okay. What happens if I graph the simplified version, 10x to the 4th over 7? What's it going to look like?
Should be the same.
It's the same. It's exactly the same. Or is it? Or is it? Let's see.
Is there
What
undefined?
Oh, there's no 0.
Yeah.
Oh.
Okay.
Why?
Okay. Well, because look at the second function. There's no x on the bottom, so Desmos doesn't know that it can't be that x can't be 0, right? That's why, but we need the functions to be identical, right? So the simplified one looks like a function with no exclusions. That's why we have to include that exclusion with our answer, because we still need to have the whole.
Do that always before we simplify?
Yes, exactly. So you want to do the exclusions before you cancel factors, because once you cancel the factors, it's going to disguise that, right? We ended up, after canceling the factors, there were no x's in the denominator, so we wouldn't have known to make that an exclusion if we hadn't done it first. Everybody get that?
Yep.
Okay, good. All right.
Don't follow me.